radioactivity. And other type of fission is induced fission. Induced fission means once the fission is initiated, then after that it will be self-propagated. So, and this will be self-propagated either by proton, either by alpha particle, either by neutron. So in our syllabus, the self-initiated by neutrons we will discuss. Okay. The fission which is initiated by neutrons, we will discuss. Okay, so basically this is uranium-235, and these are the neutrons and protons. These are the neutrons and protons inside the nucleus, because this is the uranium nucleus. So inside the nucleus there are neutrons and protons. So this is a neutron. This neutron we are bombarding on the uranium-235. We are throwing, you can say, this nucleus on uranium-235. You can use the word bombarding. Bombard the neutron on uranium-235. Now, this is a thermal neutron. Thermal neutron is having less energy. Thermal neutron means there is a neutron that is having the energy corresponding to the room temperature. Okay. So this neutron is having a less energy, and energy is approximately 0.025 electron volt, and this neutron will enter into the uranium-235. If the energy of this neutron, why we are using here the thermal neutron, because if energy of the neutron will be large, then it will pass through uranium-235. That is why we are taking the neutron of
small energy.
That is why we are taking
neutron of small energy. So neutron will enter into it. Okay. So now it will become uranium-236 because one nucleon increases. Okay. Now one nucleon will increase inside the nucleus. There are here what is here? Here are neutrons and protons. When this neutron will enter into it, one neutron will increase. Okay. So it will become uranium-236, and uranium-236 is unstable. It will break into daughter nuclei.
Okay.
And we will get 3 extra neutrons, or sometimes we will get 4 extra neutrons. Okay, so these are the daughter nuclei. So you can write this in the form of the equation. This is uranium-235 having the atomic number 92. This is the neutron bombarded on this. So neutron plus this becoming uranium-236. After that, this uranium-236 is splitting. Uranium-235 is not splitting. Uranium-236 is splitting, and uranium-236 will split into barium and krypton, and plus 3 electrons, 3 neutrons, and plus energy will be there. Okay. Energy will be there. So basically this is a nuclear fission reaction. Okay. So in nuclear fission reaction, energy will be released, and 3 neutrons also will release. After that, we will discuss the energy in fission. So we have seen this graph earlier, the graph between the binding energy per leuconion. This is in mega electron volt, and the mass number. So talking about the uranium, this is uranium, and 236 is the mass number. So basically this have the less binding energy per nucleon, that is 7.6 mega electron volt. So this uranium-236 will split into the daughter nuclei, so that these daughter nuclei have more binding energy per nucleon. So these daughter nuclei are more stable than this. Okay. So from the graph also you can see that the fission is taking place to get the stability. Okay, the fission is taking place due to get the stability. Basically, the fission of uranium-236 is taking place so that it will break into the smaller nuclei, and those smaller nuclei, when you will see on the graph, will have the more binding energy per nucleon as compared to the uranium 235. So there are some observation here. Uh, Basically, we are discussing here how much energy we will get in the fission. How much energy we will get in the fission. So in the fission, the energy we will get, one nucleus of uranium 35. If you have a one nucleus of uranium 235 on fission, it will release energy of 216 mega electron volt. On fission of one uranium 235, you will get the energy of 216 mega electron volt. 216 mega electron volt. And I told you that energy is releasing here, energy is releasing here. So corresponding to that, mass will be disappeared. I told you that whenever the mass will be disappeared, energy will be liberated. And in nuclear reaction or in nuclear fission and in nuclear fusion, there is a mass defect. There is a mass defect, and corresponding to the mass defect, the energy will be liberated. I told you not E that E is equal to mc square. So it means that if m mass is disappearing, E energy will be liberated. Okay, so here some mass is disappearing. That is why the energy is liberated in the fission reaction. Okay. So this is the simple calculation for the mass defect. I told you that if this much of energy means if this much of mass, okay, sorry, once again, I told you that on fission of uranium to one nucleus, on fission of one nucleus of uranium 235, we will get the energy of 216 mega electron. Okay, now come here. We know that if this much of energy will release, if this much of energy will release, the mass defect will be this 1 AMU. I told you that for 1 AMU mass, the energy release will be 931.5 mega electron volt in the last class. So we can calculate that in this energy, what will be the mass defect, and what is mass defect means what mass is disappearing to create this energy. So we can calculate this for this much of energy, this much of mass. Okay, so for 1 mega electron volt, this much of mass will disappear. For 216 mega electron volt, you will multiply this with 216 AMU. So approximately in releasing 216 mega electron volt, a mass of 0.23 AMU will be disappeared. Okay. So we can say that mass disappearing during fission of one nucleus of uranium 235 is 0.23 AMU. So you can now see on fission of one nucleus of uranium 235, how much mass is disappearing? 0.23 AMU mass is disappearing. Total mass of the nucleus is 235. So you can say out of, what is the total mass of one nucleus? 235. So you can say out of 235 AMU mass, only 0.23 mass is disappearing. So now we can calculate the percentage of the mass that is disappeared. This percentage, to calculate the percentage means the mass that is disappeared divided by the total mass. So this mass is disappeared mass, and total mass is this mass, and multiplied by 100. So we will get 0.1%. So basically you can say in fission reaction, when there is a fission of one nucleus of uranium 235, then only 0.1% of the mass, 0.1% of the mass of the uranium 235 will be disappeared. and we will get the energy of 216 mega electron volt. So this is all about the energy in fission. Now, from this diagram, are you getting na?
Yeah.
Here, this is having, means there is a uranium 235, and you are giving one neutron to it. So it will become uranium 236. So when you will plot that uranium 236 on the graph, so it will be like this. Somewhere here it will be. Okay, it will be
Okay.
somewhere here. You can say it will be somewhere here. So you can say that the binding energy per nucleon for uranium 236 is less. So fission will take place to achieve the stability. So there will be the fission of this uranium 236 will take place. Fission means to break this nucleus will break into smaller nuclei. So this nucleus is breaking into smaller nuclei, and those smaller nuclei will have more binding energy per nucleon. More binding energy per nucleon means more stability.
Hmm.
Now chain reaction in nuclear fission. Chain reaction in nuclear fission. Now chain reaction is sometimes very dangerous. Okay. This
Yeah.
chain reaction is used, uncontrolled chain reaction is used, can be used for making the atom bomb.
Yeah.
Okay.
Yes.
So why the chain reaction is happening? Okay,
Hmm.
see, I told you that this will be a uranium 235 and thermal
Yes.
neutron is coming, bombarding a thermal neutron, and this thermal
Yeah.
neutron will enter into the nucleus uranium 235, nucleus of uranium 235, and then it will break into daughter nuclei,
Yeah.
krypton and barium, and we will get 3 neutrons. So basically we will get 3 neutrons after the fission of this. 3 neutrons we will get, but in a sample we have millions of uranium nucleus.
Yes.
Okay, one nucleus is breaking. Okay, one nucleus is breaking. 3 neutrons, 3 neutrons are releasing. Okay,
Yes.
so these 3 neutrons then again collide with another uranium 235 here.
Yes.
Again collide with uranium 235, and
Yes.
again fission takes place.
Yes.
Again fission takes place. Again 3 neutrons will release, and again you can see 3 neutrons are releasing. Again these 3 neutrons will collide with here also. If you can just propagate this reaction like this. Understanding now? Try to
Yeah.
understand what I am saying.
Yes. Sir.
Okay. Here will be the nucleus,
Yeah.
uranium nucleus. Na? Here will be uranium 235.
Yes.
So this neutron is striking, or this neutron is now will enter into this. Now
Yeah.
again the fission reaction will take place, krypton
Yeah.
and barium, and
Yes.
3 neutron again will release.
Yeah.
Again 3 neutrons will release. So these 3 neutrons will release. Now here also this neutron will also strike with the, or this neutron will also enter into the uranium 235. Again the
Yeah.
fission of that will take place. Again 3 neutrons. So this reaction will go
So
like
can you
this.
hear me?
Yeah.
Okay, sir.
My voice is okay, na?
Yes, sir.
So understanding na what will happen? Chain
Yeah.
reaction.
Yes.
Okay. Okay. So from one fission, how many fissions you are getting? 3 fissions. From
Yeah.
one fission, 3 neutrons, and those
Yeah.
3 neutrons will make 3 fissions. So
Yes.
from one fission we are getting 3 fissions. So we can say from one fission we are getting more than one fission. So basically this is the condition of the uncontrolled chain reaction.
Hmm.
Uncontrolled chain reaction, when one fission causes more than one fission, energy release. And obviously you can say when one fission, in this case here is only one fission, so
Yeah.
you will get only 216 mega electron volt of energy. Here
Yes, sir.
3 fissions are taking place, you will get 3 into 216 mega electron volt of energy. Here 9 fissions will take place. You will get the energy of 9 into 216 mega electron volt. After that 27 fissions will take place. After that 81 fissions will take place. Number of fissions will increases suddenly and
Yes,
energy
sir.
will be increases.
Yeah,
And to
yeah.
control that energy will be very, very difficult.
Yes,
So
sir.
when one fission causes more than one fission, energy release will be multiplied in millisecond, and this phenomena will happen in millisecond.
Yeah.
This reaction will be very fast reaction. Okay, so basically, this reaction is used in making the atom bomb because.
Atom. Yeah.
Okay, so I am removing this. Okay, you should know only uncontrolled chain reaction. Okay,
Okay.
now 50 kg of this is just the example. If you have a 50 kg of uranium, you can
Yeah.
generate the energy of approximately 10 to the power 15 joule. You can get the energy of 10 to the power 15 joule.
15 June.
50 kg of uranium. Basically, there was one Hiroshima
Yeah,
blast,
yes. In Japan.
Japan.
Yeah. Yeah.
Yeah. So understanding now.
Yes, sir.
So this is just the idea. Means if you have a 50 kg of uranium, an uncontrolled chain reaction will happen. So approximately this amount of energy, this very high amount of energy can be generated. Means blast.
Yeah.
Okay. So now controlled chain reaction. This is useful for us. This reaction is useful for us. Controlled chain reaction. Controlled chain reaction means one fission causes one fission. Now how it will happen? Here one fission causes three fissions, and those three
Yeah.
fissions after that causing nine fissions, and those nine fissions after that causing 27 fissions, those
Yeah.
27 fissions causing 81 fissions.
81.
After
Yeah.
that it will be actually
It
it will
increase.
become a
Yeah.
GP geometric progression.
Okay.
1 3 like this.
Okay.
3 to the power 0, 3 to power 1, 3 to the power 2, 3 to the power 3, like this. I'm not going in that. So
Okay.
control chain reaction, one fission causes one fission. So how we will achieve this? Thermal neutron, uranium 235.
Yeah.
After fission, it will give 3 neutrons. Somehow you stopped 2 neutrons. These neutrons are being stopped. These are stopped. Somehow. So now these two neutrons will not do any further fission. Only this neutron will do the further fission. So basically one fission causes one fission. Okay. So this neutron will do the fission
Yeah.
of this uranium. Now again 3 neutrons you will get. Again you have to stop 2 neutrons. Now you can see one fission
Yeah.
causes one fission, and another one fission causes another one fission. So one fission causes one fission, controlled chain reaction, and control amount of energy we will get. We will get the
Sir,
energy
this
at
is
constant
used
rate.
in power plants, right? Nuclear power
Yeah,
plant.
nuclear reactor. This is used
Yeah.
in nuclear reactor. Basically,
Yeah.
nuclear reactor is used for
Yeah.
the electricity generation. Okay.
Yeah.
So at least in India, I can say I am not sure about the exact data. It is approximately 10% of the electricity is generated by the nuclear uh, reactor. Basically, this is not used much for the power generation because this is very dangerous phenomena. Means to
Yeah.
control that much of energy is difficult. Okay,
Yeah.
there are so many blasts also.
Yeah.
There is Chernobyl
Yeah.
blast,
Chernobyl.
I think.
Yeah. And
Chernobyl
even in
blast is,
Japan also.
yeah. There is one more blast, I think. I do not know about that, but I want to say that to control this much of energy is very difficult. That is
Yeah.
why the nuclear power is just, I think, according to me, it is just right now we are here. So this is just beyond us, the scope of us. Okay,
Yes.
right now. Okay,
Yeah.
we cannot control that much of energy in a proper manner without any disaster.
Yes.
So now, after that, energy radiated at a constant rate. So this is used in the nuclear reactor. and nuclear reactor is used for the electricity generation. Okay, finish. Now it is. This is looking like this is very easy. Means
Yes.
means we are just throwing one neutron very easily. Oh,
Yes.
what is this? Just a minute. We are throwing one neutron, and this neutron is entering. Okay,
Okay.
and three neutrons we are getting. Basically, what we do not want this.
Yeah.
I do not want this. I want only this.
Yeah.
Hmm?
Sir, your
We
voice is
thrown one
lagging.
neutron and voice is lagging.
Yes.
Okay. Okay. So we are throwing one neutron. Okay, thermal neutron, and this thermal neutron is entering into this. Three neutrons releasing. Somehow we stop two neutrons, and again we have stopped two neutrons. We are getting the control reaction. But there are certain difficulties. Okay, in practical life, in practical cases, there are certain difficulties. So difficulties in chain reaction basically. So the first difficulty is the poor concentration of fuel, uranium 235. In nature, you will get isotopes of uranium. Means in nature only 0.7% you will get uranium 235. This is our fuel na, for the nuclear reaction.
Yes.
And 99.3% is uranium 238. So this can be explained by this. If in 1000 kg of natural uranium, there is only 7 kg of uranium 235 and 993 kg of uranium 238. Now you can say that we can use this for the purpose of the nuclear fission. Now there is difficulty when we will do the fission of this. Okay, so uranium 238 is non-fissile, fissible by thermal neutron. So fission of this uranium 238 cannot be done by uranium by the thermal neutron. Okay, uranium 238 can only be fissioned with high energy neutrons. Basically, the fission of uranium 238 it will take place by the high energy thermal neutrons, not by high energy neutron, not by the thermal neutrons. So high energy neutrons basically requirement of 1 mega electron volt or more energy. So basically, for the fission of uranium 238, the neutron of 1 mega electron volt energy or more energy will be required. Okay. So suppose somehow we have given the energy to this neutron of 1 mega electron volt, and here is uranium 235, uranium 238. Somehow the fission of uranium 238 takes place, and we are getting 3 neutrons. But after that also there is a problem. These are the neutrons. The neutrons that we will get after the fission of uranium 238 will be slow neutrons. Slow neutrons and less energetic neutron due to inelastic collision. In between the neutrons and you can say between the neutrons and the nucleus, there will be the inelastic collision. And in inelastic collision, the energy will be lost. Due to that, these neutrons having the less energy. So these neutrons do not have 1 mega electron volt energy. These neutrons do not have 1 mega electron volt energy, and hence they cannot sustain chain reaction. So basically, finally, we are getting 3 neutrons, and these three neutrons do not have enough energy for the further fission. And for the uranium 235, neutron of 1 mega electron volt energy is required, and these neutrons do not have the energy of 1 mega electron volt. These neutrons have the less energy. Okay.
Yes.
So means this chain reaction will not this nuclear reaction will not sustain. Instead, these slow neutrons are absorbed by uranium 238 and beta decay occurs. This is the first problem. Second problem is that the fuel uranium 235 is fissionable only by slow neutrons. One electron volt approximately, or thermal neutron of 0.025 electron volt. Okay. So this is uranium 235. This is the thermal neutron, and we are getting again neutron, 3 neutrons. But the problem is here, na? Here we are getting these neutrons, na? These neutrons have the large energy of 2 mega electron volt. So we have to slow down these neutrons so that they can do the further fission. Okay. Now after that, the next problem is the problem of the critical mass. So critical mass depends upon the geometry of the fuel and the speed of neutrons. Even slow neutrons move at 8 times of the speed of sound. If the layer of the fuel is thin, the neutrons may pass through it without causing fission. So basically, critical mass means there should be a minimum value of the uranium 235 or fuel. You should have minimum thickness or a specific type of geometry the fuel should have, so that the neutron may not pass through that. If the neutron may pass through the fuel, so there will be no fission. Okay, there will be no fission. Okay, so basically you can say that there should be a proper or limited value of the mass of the nucleus, and that mass is known as the critical mass. So basically this is the definition. There must be a limiting mass of the fuel. There must be a limiting mass of the fuel which can sustain chain reaction. There must be a limiting mass of the fuel which can sustain chain reaction. That limiting mass is called the critical mass. Basically, there should be a limiting value of mass. There should be a sufficient value of the fuel. Okay, you can say, so that can sustain the chain reaction. Okay. If that will be the less than the critical mass, so what will happen? Neutrons have the even the slow neutrons have the speed 8 times the speed of the sound. So that those neutrons will pass through the the fuel, and the nuclear reaction will not take place. Now after that, the fourth problem is the controlling the rate of the fission. Controlling the rate of the fission. If the fission reaction will become uncontrollable, so large amount of energy will be released, and to control that is difficult. So basically this is defined by the controlling rate of fission. Okay, rate of fission. So rate of fission is equal to number of fission in the present generation divided by number of fission in the previous generation. So this can be explained by this. If this is the present generation, suppose, okay, so how many fissions will take place here? With the help of this example, I can explain. If suppose this is the present generation, okay, this is the present generation. Presently, this reaction is here. Presently, this reaction is at this stage. So at this stage, how many fissions are taking place? At this stage, how many fissions are taking place? Three. So this will be the number of fissions in the present generation, means 3.
Okay.
Now previously means here how many fissions are taking place? Only 1. So K value will be 1. So K value is equal to 3 basically, and this K is greater than 1. So that is there.
Okay.
So difficulty in the chain reaction. The last point is, if K is equal to 1, K is equal to means 1 fission causes 1 fission, and that is known as the controlled chain reaction. And if there will be a controlled chain reaction, then rate of energy liberated will be constant. Okay. If K is greater than 1, I told you there. If K is greater than 1 means uncontrolled chain reaction will be there. Okay. So basically this is the controlled chain reaction, and this will become an uncontrolled chain reaction. Uncontrolled chain reaction. Uncontrolled chain reaction. If K is less than 1, so if K is less than 1 means the fission is not will take place further. number of fissions are decreasing, or rate of energy liberated also will decrease. Okay, if k is less than 1. If k is less than 1 means this value is less and this value is more.
Okay.
So it will be like that. Previously, three fissions are taking place, and at the present generation, only one fissions are taking place. Is taking place. So means fissions are decreasing, and there will be a time when the fission will be zero, and the chain reaction will stop. So this is all about the rate of the chain, controlling the rate of the fission. So this nuclear reactor, you have to do by yourself. Okay.
Okay.
Means you should take the help of NCRT.
Okay.
Okay, and there will be a diagram. So in that you will get the construction, and you will get the working, construction and working. Okay.
Okay, sir.
So in all the batches, I have given this as homework. Okay.
Okay.
After that, we will have the nuclear fusion. Now, what is nuclear fusion?
Creating of energy by
No. Nuclear fusion is basically lighter nuclei combines to form heavier nuclei. Lighter nuclei
okay.
combines to form heavier nuclei. Okay.
Okay.
So you can see here nuclear fusion. Okay, now see here. Nuclear fusion is a process in which two or more lighter nuclei combines to form heavy nucleus along with the release of large amount of energy. So the example is this. This is one nuclei. This is another nuclei.
Yeah.
This is one nuclei. This is another nuclei, and these are the lighter nuclei because mass is 1 AMU.
Yeah.
Mass is 1 AMU. Hydrogen atoms. These are the hydrogen atoms. Okay. So these hydrogen atoms are smaller nuclei. These hydrogen atoms will have a smaller nuclei, and these are combining. Okay, these are combining. So this reaction will be like this: 1H1 plus 1H1. It will be 1S2 plus. In nuclear fusion, okay, these nucleus means this hydrogen nucleus and this hydrogen nucleus are combining. So you will get 1S2, okay, plus. So what is this 1S2 and 1H1? What is the 1H2, 1H1 and 1H3? Isotopes. So another isotope of hydrogen you will get, and here you will get one positron, and here you will get one antineutrino, plus this amount of energy you will get 0.42 mega electron volt. Means, okay, you will get the energy of 0.42 mega electron volt. So but basically this is the example. Okay, this is the example how the fusion reaction will take place. So basically fusion means blending by melting. Blending by melting means due to high temperature, these two nuclei will combine. Okay. So now what is the process of the fission? Now we will discuss that. For example, here you have seen this and this are combining. This and this are combining. This and this both are combining. So when this and this are combining, nucleus of this will combine with the nucleus of this. Okay. So this is the nucleus of this, and this is the nucleus of this. Nucleus is having a positive charge, so there will be the force of electrostatic repulsion between the two. So when these nuclei will try to combine, okay, they will be repelled by the electrostatic force of repulsion. Okay, so repulsion will take place. So there, now how the fission will take place? For the fission, we want that the nuclei should be much closer so that they can fuse. But nucleus is having the positive charge, and both the nuclei will repel each other. Okay. So now here we have to bring one nucleus from infinity, means from very far distance. Okay. Far distance means a distance of, you can say, 2 centimeter or 3 centimeter will also be an infinite distance, because we want the nucleus very much closer in terms of 10 to the power minus 15, you can say. Okay. So we have to bring one nucleus from infinity far off distance to r tends to approximately 0 by doing some external work on bringing close enough. The meaning of this is, these are the nuclei, two nuclei.
Yeah.
You want to combine them, but there will be the electrostatic force of repulsion. So you have to do some extra work against that electrostatic force of repulsion.
Hmm.
So that from infinite distance they will combine, they will come closer means r tends to 0. R means the distance between the nucleus tends to 0.
0.
Now there is another force, that is known as the nuclear force. Okay, and that
Hmm.
nuclear force start acting at a smaller distance when nuclei are at a smaller distance. So that then the nuclear force will start acting. Now after that, we know that, and you should know that nuclear force is stronger than the electrostatic force. So after a certain distance, the nuclear force will become will dominate, and the fusion reaction will take place.
Hmm.
So nuclear force will begin to act. Okay, nuclear force is attractive. Nuclear force is attractive in nature, and nuclear force is short range force. Means short range force means nuclear force act at a very small distances between the nucleus, between the nuclei.
Yeah.
So nuclear force will begin to act. Okay, so nuclear force is attractive, and this is also short range force and much greater than the electrostatic force. Okay. So basically, what you have to do, you have to give the kinetic energy initially to the nuclei, so that they should move to a distance. They should be close enough so that the nuclear force start acting. So you have to give the kinetic energy to the nuclei. Okay. So
Yeah.
we give kinetic energy to nuclei. So for that, what we will do, for giving the kinetic energy to one of the nuclei, or you can say both of the nuclei, you will heat these nuclei, and due to increase in temperature of nuclei, the kinetic energy of the nuclei will increase. So we give kinetic energy to nuclei. We heat the nuclei to supply it with an energy of approximately 400 kilo electron volt. Okay. So we will heat the nuclei so as to give the energy to the nuclei approximately 400 kilo electron volt. So with respect to this energy, to what temperature we have to heat the nuclei? So you can find this with the help of this formula. Kinetic energy of a particle,
Yeah.
kinetic energy of a particle is given by half into K into T. Half into K into T. K is the Boltzmann constant. T is the temperature
Yeah.
in Kelvin. T is the temperature in Kelvin. So we are giving the kinetic energy of this. So
Yeah.
we will put the value of Boltzmann constant, and with the help of this formula we can find the temperature, and that temperature will come out to be approximately 3 into 10 to the power 9 Kelvin. So means, what is the meaning of it? The meaning of it, you have to give the temperature of approximately 3 into 10 to the power 9 Kelvin. After this temperature, the nuclear fusion will start.
Hmm.
This is very large temperature,
Yeah.
and this temperature is not present on Earth. In a controlled manner.
Okay. Hmm.
So at such high temperature, the nucleus of the gas breaks into atoms. These atoms completely ionize. So when you will give this much of temperature to the atom, so what will happen? It will break into the nucleus, and all the electrons will be removed. Okay, so
Okay.
at such high temperature, the nucleus of the gas breaks into atoms. These atoms completely ionized to bare nuclei. All electron will be removed. There will be only nucleus. Okay, an electron cloud around them are obtained. Basically, you will get the plasma state. Plasma state means
Okay.
if you have a solid, then you will heat this solid, you will get the liquid. Again, you will heat it. You will get gas. Again, you will heat to a very high temperature. You will get a plasma state. In plasma state, you will have only nucleus. Okay, this type of structure will have. Suppose
Okay.
any atom is there, to that atom you have heat to high temperature. So what will happen in the plasma state? This will be the nucleus, and here will be the electron cloud. Here will be the electron cloud. Okay, so basically
Okay.
these two nuclei now will combine, and
Yeah.
fusion reaction will take place. And
Hmm.
nuclear fusion is exothermic process. Exothermic process means the energy will release in nuclear fusion.
Hmm.
Once fusion starts, no further external heating is required, because nuclear fusion is the exothermic process. So large amount of energy will release. Okay, if large amount
Okay.
of energy, it means for the further fusion, this large amount of energy will be used again. So once it is started, after that it is self-propagated or self-sufficient, you can say.
Hmm. Okay.
Okay, so in nuclear fusion, remember that binding energy always increases till iron. That means energy is released in the nuclear fusion. We know that the energy is releasing in the nuclear fusion. So these
Yeah.
are two smaller nuclei combining to form a bigger nuclei, and here delta E energy is released. Okay, and in nuclear fusion also there will be the mass defect, and due to that mass defect, this delta E energy will release. So delta M mass will disappear in fusion, so delta E energy will release. So basically binding energy will increasing. Why? Because these two nuclei will have
Yeah.
less binding energy. These are
Hmm.
less stable. After fusion reaction, why the fusion reaction is taking place? To get, so that the nuclei can get the stability. So initially they are less stable, having less binding energy per nucleon.
Yeah.
After that, after the fusion, they become more stable. They become more stable means more binding energy per nucleon. That is why in nuclear fusion, binding energy always increases till higher. That means energy is released in nuclear fusion. So after that, the last question. Which refers more amount of energy per unit mass of the fuel? Fission or fusion? Fission or fusion? So tell me, do you have, if you have any idea?
Hmm. Fission.
Mm, okay, we will check which have the more energy. So we for this there is a requirement of data. Okay, for this there is a requirement of data. Uh, I told you that Shabruddin, oh, sorry, Ziyad, is my voice okay
Yes.
now?
Yes.
Now,
Yes, sir.
now it's okay now.
Yeah.
Okay, so what I told you in fission, in fission, for the fission of one uranium nucleus, for the fission of one uranium nucleus, 216 mega electron volt energy we are getting.
Yeah.
Were fission of one uranium nucleus, hmm, one uranium nucleus, how much energy we are getting? Approximately we are getting
Yeah.
216 mega
Elect-
electron volt. So we can take this value as approximately equal to 200 mega electron volt. Okay, so you can take this is on, this is fine. So in the fission of one uranium nucleus, this much of energy you are getting. And which nucleus was breaking? Uranium 236 was breaking, na? So means for the fission of 236 AMU mass, uranium 235 was getting one neutron. It becomes uranium 236. After that, it is breaking. So basically, this much mass, this 236 AMU mass, giving you the energy of 216 mega electron volt. Now, how much energy the 1 AMU mass will give in the fission? It will be 216 divided by 236, and this will be equal to 0.85 mega electron volt. So 1 AMU mass in fission will give 0.85 mega electron volt. So this is 0. Mega electron volt per AMU. So in fission, what we are getting from the 1 AMU mass? From the 1 AMU mass, we are getting 0.85 mega electron volt, okay, of energy. Now in fusion, see the fusion reaction. Oh, after that, oh, there is one more. This reaction is left. Exact nuclear fusion reaction. So basically, the fusion reaction will take place in 3 steps. Okay. These two hydrogen atoms or these two hydrogen nucleus will combine, and this hydrogen is having one proton, this hydrogen is having one proton, and after that it will become 1s2, one positron, one antineutrino plus this much of energy, and this is having one proton and one neutron. Now after this we have this, so this again will combine with 1h1 and it will become helium 2 3. Okay, this is atomic number, this is mass number, and after that there is a gamma particle. Okay, and plus this much of energy will be released. Okay, after that this helium will again combine with helium. Okay, it will become helium 2 4. Okay, 2 3 helium means helium of atomic number 2, mass number 3 will combine with the same helium. Okay, and it will become helium 2 4, and there is a release of 1h1 and 1h1 having one proton and one proton, and this much of energy it will release. Okay, now if you want this in only one step, all these three reaction in one step, so what you should do, you should multiply this equation by 2, you should multiply the second equation by 2 and add those two equation with third equation, you will get the final equation of fusion. Equation of fusion. So basically, this is the final equation of fusion. So 4 hydrogen atoms plus 2 electron, we will get helium 2 4 plus 2 antineutrino. Okay, plus 6 of gamma plus 26.7 mega electron volt. So you can say 4 hydrogen atoms are giving this much of energy, 26.7. 4 hydrogen nucleus, these are 4 hydrogen nucleus on fusion will give 26.7 mega electron volt of energy. So in fusion, we can say 4 hydrogen atom, 4 hydrogen atom, so hydrogen nuclei will give the energy of 26.7 mega electron volt. So for one hydrogen atom having a mass of 1 AMU, so 4 hydrogen atom is having a mass of 4 AMU. So 4 AMU mass is giving the energy of 26.7 mega electron volt. So 1 AMU mass will give the energy of 26.7 divided by 4. This will be equal to 6.7 mega electron volt per AMU. So in fusion, we are getting 1 AMU mass is giving the energy of this, and in fission, 1 AMU mass is giving the energy of this. So which will give more energy, fission or fusion? Fusion, na?
Yeah.
In fusion, 1 AMU mass is giving 6.7. In
Yeah.
fission, 1 AMU mass is giving 0.85. So you can
Yeah.
write in fusion much more energy is there, much more energy than fission per unit mass. Per unit mass of fuel. So in fusion, we will get more energy as compared to the fission per unit mass. Okay. So now you should take the screenshot from here.
Done.
Okay, Azan time, please wait.
Okay, sir.
Okay, so now take the screenshot.
Done, sir.
Okay.
Done, sir. Yeah, done. Done, sir. Done. Yeah.
Okay.
Yes.
Okay.
Okay. So can I take screenshot of third point? Yeah, done. Yeah.
Just a minute. Take the screenshot.
Yeah, done. 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 Done.
Just wait.
Okay.
Okay. So now please take this screenshot.
Done.
Okay.
Done.